What really happens inside a missile when it's launched? Asterisk asterisk, have you ever stopped to wonder what actually happens in the fraction of a second after a missile launch is triggered? Most people picture a simple explosion followed by a rocket flying through the sky. But that mental image couldn't be further from the truth. What actually unfolds inside a missile from the moment of ignition to the moment of impact is one of the most precisely engineered sequences of physical events that human civilization has ever produced. Every millisecond is choreographed. Every component is a compromise between competing forces that would tear the system apart if any single variable drifted out of tolerance. This is not a weapon. This is applied physics moving faster than you can blink. The fundamental problem that missile engineers have had to solve for decades is deceptively simple to state but almost impossibly hard to execute. How do you create a system that generates enough force to accelerate hundreds of kilograms of metal to speeds exceeding Mach 3, navigate autonomously through an atmosphere that is actively trying to destroy it, and deliver a precisely calibrated release of energy at exactly the right point in space and time, all without any human intervention once the trigger is pulled? The answer is a layered stack of thermodynamic, aerodynamic, electronic, and materials engineering solutions that interact with each other in ways that took generations of scientists and engineers to understand. And it all begins in a moment so brief that by the time you register that the missile has left its launcher, the most critical phase of its existence is already over. The first thing that happens when a missile is launched is ignition, and ignition is where the first great paradox of missile engineering lives. The propellant inside a solid fuel missile, which is the most common type used in military applications, is not a liquid or a gas. It is a dense, rubbery solid that looks more like a block of industrial material than anything you might associate with an explosion. The most widely used formulation is a composite of ammonium perchlorate as the oxidizer, aluminum powder as the fuel, and a polymeric binder that holds everything together and gives the propellant its physical structure. When an electric current passes through an igniter embedded in this material, the surface of the propellant begins to burn. And here is the critical distinction that separates a missile from a bomb. The propellant deflagrates, it does not detonate. Detonation is a supersonic combustion wave. It releases all of its energy almost instantaneously, and that is precisely what makes explosives so destructive. Deflagration, by contrast, is a subsonic combustion process. The flame front moves through the propellant at a controlled rate that the engineers have designed into the geometry of the grain, which is the term for the shaped block of solid propellant inside the rocket motor. The shape of the grain determines the burn surface area, and the burn surface area determines the thrust curve, which is the profile of how much force the motor produces over time. A star-shaped grain cross-section exposes more surface area and produces higher initial thrust. A cylindrical bore that burns from the inside out produces a progressively increasing thrust as the bore widens. Engineers choose grain geometries the way composers choose time signatures. The shape determines the rhythm of the entire flight. The combustion process inside the motor generates gases at temperatures that can exceed 3,000 degrees Celsius. At those temperatures, the gases expand with violent force and are channeled through the only exit available to them, which is the nozzle at the rear of the missile. And the nozzle is where the second great piece of engineering magic happens. It is not a simple hole. It is a precisely shaped converging-diverging passage known as a Laval nozzle, named after the Swedish engineer who first understood its properties in the late 19th century. In the converging section, the gas is accelerated as it is squeezed into a smaller cross-section, exactly the way water speeds up when you narrow a garden hose with your thumb. At the narrowest point of the nozzle, called the throat, the gas reaches exactly Mach 1, the speed of sound. In the diverging section that follows, a counterintuitive thing happens. The gas continues to accelerate, reaching speeds of Mach 2, 3, or even higher depending on the expansion ratio of the nozzle. The key insight is that at supersonic speeds, a widening channel accelerates gas rather than slowing it, because the flow dynamics have fundamentally changed. If an engineer miscalculates the divergence angle of the nozzle by even 1 degree, the missile loses between 5 and 10% of its thrust efficiency. In an interceptor missile designed to hit a target moving at high speed, that margin can be the difference between a kill and a miss. The nozzle also has to survive its own environment. The gas flowing through it at Mach 3 or higher is not clean air. It contains particles of aluminum oxide from the combustion of the aluminum fuel, and those particles scour the nozzle walls with abrasive force. The throat of the nozzle, the most stress point, is typically made of carbon-carbon composite or tungsten, materials that can withstand thermal and mechanical loads that would vaporize ordinary metals. Some nozzles are designed to be expendable and accept a controlled amount of erosion during the burn. The engineers calculate exactly how much material will be removed and account for it in the nozzle geometry, so that the performance remains within acceptable bounds even as the nozzle slowly destroys itself. Once the missile has cleared its launcher and is flying through the atmosphere, a completely different set of physics problems takes over. The aerodynamic forces acting on a missile at supersonic speeds are not simply larger versions of the forces acting on a slow-moving aircraft. They are qualitatively different. At supersonic speeds, a bow shock wave forms in front of the missile, a nearly instantaneous compression of air that releases heat. The boundary layer of air flowing along the skin of the missile becomes a region of intense thermal stress. At Mach 3, aerodynamic heating can raise the surface temperature of the missile to over 300 degrees Celsius. At Mach 5 and above, which is the domain of hypersonic missiles, the heating becomes so severe that it can exceed the melting point of aluminum and approach the limits of even high-performance steels. This is why the nose cone and leading edges of fast missiles are made of ablative materials, substances that are engineered to deliberately sacrifice themselves layer by layer, absorbing heat through the process of vaporization and carrying it away from the body of the missile. The same technology that protects the heat shields of spacecraft during atmospheric re-entry is protecting the guidance electronics inside the nose of a missile flying at a fraction of that speed. The missile is, in a very literal physical sense, burning itself from the outside to survive on the inside. At the same time that the missile is managing its thermal environment, it is also actively managing its trajectory. And this is where the engineering challenge becomes almost philosophically interesting, because a missile in flight is a system that must navigate a world that refuses to stay still. The target it is pursuing may be maneuvering at high speed. Crosswinds at altitude can push the missile off course. The density of the atmosphere changes with altitude, altering the aerodynamic forces on the fins and control surfaces. And the missile must compensate for all of these disturbances in real time, without any external input, relying entirely on the sensors and processors it carries inside its own airframe. The foundation of missile guidance is the Inertial Measurement Unit, or IMU. This device contains a set of gyroscopes and accelerometers that measure every change in the missile's velocity and orientation with extreme precision. The accelerometers detect linear acceleration in 3 axes. The gyroscopes detect rotational rates around 3 axes. By integrating these measurements over time, the missile's onboard computer can reconstruct its position, velocity, and attitude in 3-dimensional space without any reference to the outside world. There is no GPS signal required. There is no communication with a ground station. The IMU is essentially a small mechanical model of the universe that the missile carries inside itself, and it uses the laws of Newtonian mechanics to deduce where it is and where it is going at every instant. But the IMU has a fundamental limitation that no amount of engineering has been able to fully eliminate. It accumulates errors. Every integration of a measured acceleration introduces a tiny numerical error. Over time, those errors compound. A missile that relies solely on inertial navigation for an extended flight will gradually drift from its intended path, and the longer the flight, the larger the drift. This is why modern missile guidance systems are hybrid architectures that fuse inertial measurement with external correction signals. A radar seeker in the nose of the missile continuously scans the forward hemisphere, looking for the radar return signature of the target. An infrared seeker detects the thermal signature that any warm object radiating heat into a cold sky will produce. Some missiles carry terrain-following systems that compare the radar image of the ground below to stored digital maps, correcting the inertial drift by recognizing known landmarks. The data from all of these sensors is combined by a guidance algorithm that performs a real-time statistical estimation of the true position and trajectory, constantly trading off the reliability of each sensor source against its noise and latency. This kind of sensor fusion is one of the most computationally demanding tasks that an embedded processor can be asked to perform, and it is happening aboard a vehicle that is flying at several times the speed of sound and experiencing vibration levels that would destroy most consumer electronics. The control system that actually steers the missile is equally impressive. Early missiles used aerodynamic control surfaces, fins that could be deflected by actuators to generate steering forces, exactly the way an airplane uses ailerons and elevators. But aerodynamic controls become progressively less effective as a missile climbs to high altitude, where the air is thin, and they are completely useless in the brief moments at the very beginning of flight before the missile has built up enough speed to generate meaningful aerodynamic force. Modern missiles address this with thrust vector control, which means physically tilting or deflecting the exhaust plume from the rocket motor to steer the missile. Some systems use a movable nozzle that pivots to redirect the thrust. Others inject a gas into one side of the exhaust stream to deflect it. Thrust vector control works at any speed and any altitude, from the moment of launch until the propellant is exhausted, and it is why modern missiles can pull maneuvers that seem to defy intuition, turning sharply at high speed in ways that no purely aerodynamic aircraft could match. As the missile approaches its target, the final phase of guidance takes over, and this phase is in many ways the most sophisticated of all. The seeker in the nose of the missile is now locked onto the target and tracking it continuously. The guidance law that translates the seeker output into steering commands is typically a variant of proportional navigation, a principle derived from the mathematics of pursuit curves. The missile does not simply point at the target and fly toward it, which would be inefficient because the target is moving. Instead, the guidance law commands the missile to null out the rate of change of the line of sight between itself and the target. If the line of sight is rotating, it means the missile and target are on a collision course that is not converging, and the missile steers to correct that rotation. When the rate of change of the line of sight reaches zero, the missile and target are on a true collision course, and no further steering is needed. This is an elegant and mathematically optimal approach to the interception problem, and it is one of the reasons that modern missiles are so difficult to evade. A target that maneuvers to break lock causes the line of sight to rotate, but as long as the missile seeker can track the target and the missile has enough maneuverability to respond, the guidance law will command the corrections needed to maintain the intercept. The final event in the missile's life is the detonation, and even this is not as simple as it might appear. Most warheads on modern missiles are not designed to destroy targets through direct physical impact alone. The lethal mechanism is fragmentation. The casing of the warhead is engineered to break apart in a controlled pattern when the explosive charge detonates, generating a cloud of high-velocity fragments that travel outward at speeds that can exceed 2,000 meters per second. To maximize the effectiveness of this fragmentation pattern, the warhead must detonate not at the moment of impact, but at the optimal standoff distance from the target. The device that determines this moment is the proximity fuse, which is typically a small radar transceiver built into the nose of the warhead. It continuously measures the distance to the target by timing the round-trip travel of its radar pulses. When that distance falls to the point calculated to maximize the area covered by the fragmentation pattern, the fuse fires the detonator. The entire sequence from fuse activation to complete warhead detonation takes place in less than a millisecond, which at missile speeds corresponds to a distance of less than a meter. The precision required to detonate a fragmentation warhead at exactly the right moment, at a target that may be a fast-moving aircraft or another missile, is itself a remarkable piece of engineering. What you are watching when you see a missile launch is not just a weapon being deployed. You are watching solid-state chemistry converting stored chemical energy into kinetic energy through a controlled thermodynamic process. You are watching aerodynamic engineering managing the interaction between a solid body and a compressible fluid at speeds where the intuitions built from everyday experience completely break down. You are watching embedded computing systems performing real-time sense of fusion and optimal control calculations on hardware that has been engineered to survive environments that would instantly destroy ordinary electronics. You are watching material science at its absolute limits, with structures that deliberately consume themselves to protect the systems they house. And you are watching decades of accumulated human knowledge in mathematics, physics, chemistry, and engineering, compressed into an object that weighs a few hundred kilograms and lives for a few minutes before ceasing to exist in the accomplishment of the purpose it was built for. The next time a missile launch appears on a screen in front of you, pause for a moment before the image moves on. Because in the time between the ignition flash and the moment the missile disappears from view, an entire universe of physics has already played out inside that airframe. And almost none of it is visible to the naked eye.